All right, let's begin. Welcome to today's Micrographics webinar. Today's topic, Inventor Nastran Nonlinear Analysis. Okay, so this is going to be a fairly short webinar. It's not going to go into that much detail. It is not a substitute for any training that we would do, but it's just to get an idea of where we stand and how to go about understanding what exactly nonlinear analysis in Inventor Nastran is all about. Okay, so the purpose of today's webinar is to discuss the steps to analyze stress that may exceed the maximum yield stress of the material. Now, I know that was a mouthful, but basically what we're saying is that in certain loading situations, we have our design, we apply some loads to it, and we will find that we are not sure whether those results that we are achieving are correct. And the simple reason is that we don't know whether it has reached the yield stress or not without first doing the analysis. Right? And as a result, we can have wildly out of spec results. So let's discuss the agenda of how we're going to get there. Firstly, we're going to take a look at getting started, what you need to know. We're going to do a quick Inventor Nastran overview. How do I know when to use which analysis? Okay, in this particular webinar, the scope of this short webinar, we're just going to discuss linear static and nonlinear static. That's the main focus. And I think once we understand the differentiation between the two, we can better make decisions on how to analyze nonlinear systems. Okay, we're going to talk about setting up the model. We're going to talk about the types of materials, constraints and loading. And then we're going to speak lastly with a live demo of how to interpret those results and how any changes you make will affect the results. Okay. At the end, we're going to have a Q&A. So if you have any questions, you can discuss it then. Or if you're curious during the webinar, you can always just type it in and we will do our best to answer it. Or if not, we will answer it at the very end. Okay, so getting started, we're going to look at a problem definition. We want to perform an analysis of loading conditions on design, but the stresses may exceed the maximum limits. What do I mean by maximum limits? Well, we'll take a look at the stress strain graph in a bit. So first we need to ask ourselves, what information do we require from this study? If we require simple maximum deflections, it can become fairly simple. We just put in the values and put it through the Nastran solver, and we should get out some values. But how do we know that our values are correct? Well, this is where it starts to get a bit gray. We really can't know until we do some comparisons. And lastly, the last question we should be asking ourselves is the model simplified as much as possible? So for example, if you are analyzing a jig crane, you won't necessarily need to model every single part that you want to analyze. You just want to identify the specific area that you suspect is going to fail and apply a load, a constraint, and where any possible joints or contacts meet. So just taking a look of Inventor Nastran, an overview. So we know that Inventor Nastran uses the finite element method. Right? So in layman terms, it breaks the model up into little pieces called elements, right? And we know at the ends of each element, we have things called nodes, right? There's a couple of ways of drawing this. In 3D, you get generally quadratic tetrahedral elements. When you're doing this kind of finite elements analysis by hand, which is very tedious, you'd find that you'll often have to work in 2D and work with basically segments of lines and that sort of thing. Okay. On the right-hand side, we have, just going to minimize this. On the right-hand side, we have the regular stress strain curve. Right, and this is essential to understanding where our capabilities with linear and nonlinear start and end. So we know that on the one axis, we have stress, which is basically force with respect to the cross-sectional area. So if you think about a steel rod, and you're pulling that steel rod from opposite ends, a solid rod, and it has a cross-sectional area of, let's say, 5 millimeters squared, right? You can apply a load onto that, but the effect of that load is different to that of a steel rod with, let's say, a 10 millimeter squared cross-sectional area, right? So stress is nothing but force with respect to area. Okay. On the other side, we have strain, which is basically the percentage change. So it's the change in the length over the original length of that steel rod. Okay. And why we need to analyze this is because you will notice that from the graph, in the first part, you will see that there will be a linear relationship between the two, meaning as you increase the stress, there's a linear change in the strain, right? But that only goes so far up until a certain point. You'll find that at that point, it reaches what's known as the yield strength. At this point, if I let go of the load, right, that steel rod will return to its normal preloaded length, meaning that it's elastic. As if you pull something, it will return to its normal shape. Once it goes beyond that point, the yield strength point, it's going to start to permanently deform. And you'll find that the amount of change in this length varies depending on how much of stress you put. And if you follow the graph up until this point, it's when it reaches ultimate strength or ultimate tensile strength. And here, the material will begin to neck. So if you look on the internet, you'll find little pictures of steel rods that are necking, which basically becomes narrower and narrower until finally, if you add a little less stress and less stress and less stress, you find that it reaches a point where it can't change its length anymore, and it completely fractures. Okay, so what was the point of explaining all of that? Well, the point of explaining all of that was understanding that for linear static analysis, you're only dealing with the region that's in a straight line, a linear relationship between the force that you apply and the change in the length of your part. Okay, beyond that, you're going to have to consider nonlinear analysis. Right? So how do you know when we're doing that? Well, okay, the line, the defining line between the linear and nonlinear is gray at best. Okay, so we really don't know until we perform some sort of analysis. Generally, we are referring to the elastic region of this graph. We're referring to that area. And in linear static analysis, it's key to assume the following are happening. First thing is that the displacements and rotations are small. So if you have a load on, like I said with that steel rod example, we're talking about 0.001 of a change in length. Same with rotations. If you're applying a load that's perpendicular and not parallel to the geometry, you'll find that the rotation should be really, really small, 0.000 theta, right? We're assuming also that these supports do not settle, meaning they don't move or they don't sink anymore. The material remains linear throughout our analysis, meaning that it doesn't approach any yield stress. And this is where we will know that we're dealing with stresses that are a lot less than the maximum yield stress. Right? And lastly, we are assuming that the loads, all of the magnitude, orientation, distribution remain constant as the structure deforms. Right? I'll dive into a little more of that just now with some pictures. Right? But basically, once the stress goes beyond that point, it can affect the model in various ways. So how can things change? How can it affect the model in various ways? Well, before you read all this wall of text, let's take a look at these three diagrams. Suppose you were doing an analysis on the extreme left picture, right? You're applying a load on some sort of design. That load will, or that horizontal member will deform at some stage. Now, if it's within the elastic region, that deformation is fairly small and shouldn't affect the resulting increase of load. So we can still assume if it's very small deflection, a very, very tiny slope, we can still assume that it's 2 uprights and 1 horizontal and that the model hasn't changed. However, once you go past the yield strength, you start to go into permanent deformation. And once your deflection becomes really, really large, as shown in our diagram here, you'll find that now you're no longer analyzing 2 uprights and 1 horizontal. You are now analyzing 2 uprights and 1 curved beam. Remember, this curved beam no longer has the same strength as that horizontal beam. So it is, in fact, I've written here, technically a new problem. So if you increase the load further than this, you're not doing yourself any favors by assuming that it is still a linear relationship. You're going to have to consider that things have not changed. Okay, so just to read that wall of text, displacements and rotations may become large enough that equilibrium equations must be rewritten. So basically, if you consider this example, the load has now changed how it's acting. You can see now the load is now affecting these uprights in different ways. It may be pushing or pulling upwards depending on how it's joined to those ends there. Okay, so it can be quite tricky. Large rotations cause pressure loads to change direction and also to change in magnitude. That's correct. So we will find a direction and magnitude change at the contact areas. Okay. Elastic materials may become plastic, or the material may not have a linear stress-strain relation at any stress level. So basically, if something like steel or aluminum used to be elastic, it will now become plastic and permanently deform and change as you add more and more stress. Okay, part of the structure may lose stiffness due to buckling or material failure. So you can imagine these upright members, if they had some weakness going in the horizontal direction, now that this is curved, it's going to affect that as well. Okay, adjacent parts may break or make or break contact with the contact area. So as we said, depending on how you define your contacts here between the horizontal and vertical members here in this example, you will find that either they will separate and change the problem completely, or they will completely break if they are bonded and there's too much stress at that point. Thus, a nonlinear effect can be broken down into 3 main categories, right? It's basically geometric changes where you have large displacements, and that changes the problem into a new problem. Material changes where as you add more and more stress, the material properties don't behave the same way, right? So nonlinear stress strain curves. And lastly, boundary conditions, basically where the parts make contact with each other and they affect the entire problem by either breaking or coming apart and affecting the other members not as expected. So how do we know which to use? Well, that is the reason Inventor Nastran has multiple studies. It allows comparison of results, and when you know that either A, you're having a geometric, it can fall into the category of geometric large displacement. So you're having a geometric disparity, right? Or you're having a where you know that your stress is far exceeding your yield stress, which means it's going into nonlinear mode. Or you know for a fact that you are affecting the strength of that bond between the two. Okay. So this allows you, when you create multiple studies, it allows comparison of results, allows you to make quick changes and have a whole host of things that you can just drag and drop into your study. And it aids in better design. You can go back to your model and design accordingly to make sure that it withstands the strain. So you need to be looking at deflection, material yield stresses, and surface contacts. So how would we go about setting up our model? Firstly, we need to ensure that your design is an assembly of components. But I've seen many clients that are trying to analyze a multi-body part, and it just does not work because it will not allow you to select multiple materials or multiple components or surface contacts. Okay. Then you need to determine whether geometric changes are going to invalidate your result. So what does that mean? Well, if you go back to this, we need to determine that, okay, does a 5 mil deflection here mean that I'm now completely changed and I can no longer assume that this is a straight horizontal, or is 5 mil acceptable? You're going to have to decide as the person doing the study. You're going to determine your constraint points, so not just where they are, but also what types of constraint. Like we said, they can either be bonded, separated, or whatever. We will come to that in the next few slides. And lastly, yes, like I said, determine the surface contacts. Right? Also, I've just noted a hint here. Again, something many people are not aware of is that you can place a load anywhere on your model as long as there is a node there. So what happens if there is no node on the place you want to put a load? Well, if there's no node on that area, you can simply use your mesh control settings to create a node on that point where you are applying the load. And I'll show you exactly how to do that shortly. Okay. Then we're going to consider the types of materials. So material properties are really important. Right? I've just got an overview here of things I've found in textbooks and on the internet. And we're basically looking at FEA material properties. And you can see for all these different properties make a difference in determining whether you're going to use linear or nonlinear analysis. Right? So remember that the graph is going to be different for a ductile material as it is for a metal material, or something that is similar to a ferrous metal, like anything containing iron, or something like aluminum. Right? And you can see the distinct difference in the shape of the graph. Okay. And lastly, before we get to the live demo, we are going to talk surface context and just 3 main definitions, super simplified. Right? So remember, what are surface contexts? They determine how one component affects another one attached to it. Right? So you can have 3 main groups, and like I said, super simplified. Bonded will assume that all are one solid piece. So you will see that now in the example that I do in the demonstration. Sliding assumes that the components that are laying next to each other or attached remain in contact, but do not lose, but can slide across each other. Right? And separation assumes that components can lose contact. Right? Now there's combinations of these which you can have. Sliding, no separation, mean that they can slide, but they will never come apart from each other. Okay, and you can have separation, no sliding, meaning that it will separate, but it will not slide across because it is fixed somehow. Okay? So let's go to a demonstration of Inventor and look at how we can achieve or how we can compare analysis and why it's important to understand the difference. So if you look at the model here, I'm just going to say finish that analysis for now. I just want to talk about the model for a bit. Okay, so basically what we're discussing is 2 different types of materials. Right, so you can see I've got 3 different solids, and I'm deliberately putting 2 here as steel uprights and 1 as plastic. Right? Now I've done them just for the appearance sake, so you can see here I'm just got those are going to be steel, but obviously we're going to have to define that in our Inventor Nastran environment. So we go to environments, Inventor Nastran, and let that load for a few seconds. Okay. So now that we are in our analysis mode, I'm just going to delete this so we can start totally from scratch to see that I'm doing it as we go along. I've already made some materials here. I made one that's called plastic and one that's called steel, and I'm going to apply it to these. How do we do that? Well, we can go to our idealizations, and we can simply right click there and say idealizations. I'm going to say that the plastic one applies here, right? And we'll call that right. So now we've got plastic, and it refers to just that. Okay. Secondly, I'm going to do another idealization for the steel, and I'm going to say it applies to these. Remember, we're working with analysis 1, and I'm deliberately keeping it as a linear static, just to show you the very basic of what will happen if we increase and increase the loads. Okay, so here we have our materials done. So one of the steps is already done. Next thing I need to do is define that it's fixed down here as my constraints. So I've already done it here in my model. I've created a constraint. If I look at it, that's what it is. So I'm simply going to drag it into the study and say, okay, yeah, we're going to have that constraint. So those are fixed, right? And then we're going to apply a load to this. We're going to apply a load at the center there. And notice I've just simply drawn a sketch with point, and I'm going to tell it use that point to apply my load. So make a load there. Point load 1. Okay. Right. I'm going to tell it that the selected entity is that point. It's going to go in the y direction. You can see the green arrow there, and it's going to go negative 500 newtons. Now I've chosen 500 newtons just so we can get a tiny deflection on this sort of scale. Right? And then we're going to increase it and see differences as we go along. So that's acting on that, and let me just make it visible so that we can see it. Okay, and it's acting on that component, and we are done. So now we've got everything. However, we need to mesh, and we still need to define exactly how this model is going to behave. Because remember, we said that surface contexts are important. So what do we mean by that? We've got 3 components in here. Okay, and we didn't define how they are related to each other. So what we're going to do is we're just going to use the auto surface context, right? Auto context solver. It's going to find all the contexts and assign general settings to them. So we're going to say, and you'll see that appeared surface context. It found that contact on one side and on the other side. If I edit them, you'll see that it is by default placed them as bonded, meaning that it assumes, remember from our slides, it assumes all of them, or it assumes that the 2 are one solid piece. Right? And I'm going to leave it like that for now, even though that's not true in this particular case, but I'm going to leave it like that just because we're worried about the analysis for now. Right? So basically, it's not going to slide, it's not going to come apart, they're not going to go like that, like how you saw it on my little diagram in the slides. They're simply going to remain fixed, and it's only going to bend starting from afterwards, according to the material properties. Right? So the last step, is, of course, is we need to create a mesh. So mesh this model. So I'm going to say generate a mesh, and you'll find that by default it puts in a mesh, and in this mesh, because they're symmetrical and I put or it's selected an appropriate size for me, you'll find that a node appears directly at the center, which is where my load is. I just want to enunciate that properly because node sometimes sounds like load. Okay, so basically the load I've applied is at the center, and there's also a node, N-O-D-E, at that point as well. So it will work. However, I've also created a secondary point here. What happens if I wanted to put in a load there? Well, if you can put in a load there, but it will give you an error. And I'll circle back to that and show you how to actually apply a load there. But let's just continue with the analysis for now. Okay. So I have all the information. I've fed the solver all the information. It doesn't look like there's anything else that I needed to do. Steel, 2 steel uprights, 1 plastic. Let's run and see what Nastran comes up with. Remember, we are doing a linear static, not a non-linear. We're just doing a linear for now. And it says Nastran solution complete. Okay. We're just going to look at displacement for now. It's easiest to understand, right? And we're going to see, obviously, the exaggerated model. Remember, this is bonded contact, meaning that they can't come apart, which is why they didn't go like this, like a smiley face. They stayed in contact until that point where all the stresses that are there and the maximum displacement adding down here. If you look at the stress, you'll find that you have pockets of stress around where it is meeting there. Okay. So that says 0.5 millimeter, right? So if we look at our, this is obviously, like I said, an exaggerated view. If you look at your options and you change it to actual, we'll find that this is quite realistic. We've got 2 steel uprights, you've got a plastic with 500 load, and that's how 0.5 deformation or displacement rather will look in that scenario. However, what happens if, let's go back to our model, I now exceed, or I'm using a larger load. So let's change our point load. Let us change it to tenfold, right? So this is 5,000 Newton going downwards, right? And we'll run that simulation. Now, here we find that the displacement is quite large, right? At this stage, you should become suspicious. You say, hey, I've now exceeded the load and the stresses. And let's look at the stress. The stress on the x normal axis or on any particular axis, right, is approaching what is above normal. And you can just see that our first rule from our slides, that if the displacement is becoming large, you're going to know that, hey, this is now affecting the geometry of the model, and it's probably not very accurate. So what I'm going to do now is simply return. Notice that there was a 5 mil displacement. Let us duplicate this analysis. And we'll call it non-linear static. Okay. So the second analysis is I'm going to change it to non-linear, continue with the 5,000 Newton load, and we're going to be non-linear static. And we're going to see that now it's going to take into account the fact that the geometry changes with everything else. So everything else remains the same, including the load. Remember, there we go. It's negative 5,000 Newtons. And now we're going to run right. Okay. Solution complete. Let's look at the displacement. That's so you can see not much difference here because, well, 5 mils wasn't that much so we can determine that our geometry wasn't really affected that much. Although, let me just constraints. I'm just checking everything is correct. Right. So we can see that even though we have a non-linear static, we're getting the same result because those kind of loads on this type of beam doesn't really affect the geometry that much, and hence it doesn't need to take anything into account. So let us go back to activate the old one, and we'll try and change the loads a bit more. Let's see if we can change the load to 50,000. We're gonna run this. Okay. So we've got a 50 millimeter displacement, which is, well, basically 5 centimeters. So that should be big. Now this should start to change the geometry. So let's see if we get a different result on the non-linear static using a 50,000 load. So you can see now there's a slight disparity between what we're getting. So as you increase the load, because the geometry is changing, you'll find that basically you find that your displacement is changing quite significantly. You're getting a difference of 2 millimeters just by using the correct type of analysis. So as the geometry changes, you can find that. Now, how do I know that those are values that are going to give me changes? Well, like I said, from our slides, we can understand what our yield stress is for the material. So if you look at your materials for the plastic, you can find that, look, there it is. You can find a whole bunch of these information populated. And in particular, we can look at Poisson's ratio, which is that, and the allowable stress. So the maximum allowable stresses, then the yield stress, and all of those kind of things. So we'll find density, maximum yield stress, etc., etc. So if I know that the maximum allowable stress is going to reach in my analysis that point, then I know that the geometry is going to be changed a lot, and I'm going to need to run a nonlinear analysis, right? Otherwise, you can simply do this using Inventor's stress analysis tools. Okay. So lastly, what I want to do is I want to circle back to that concept of using a different load. So like I said, oops, sorry, I seem to have exited the whole thing. I said that if we want to have a different load that's, let's say, pointing there. So in my analysis, let's look at the nonlinear. I'll activate that. And I want to add in a load in here that is not this one. I'm going to remove this one. I want to add in one that's a different, I'll say new load, negative 5,000 or 50,000 or wherever it is. And I'll say, okay. Oh, correct. There we go. I want to say, right, it's acting on that point. 0.4, and let's just display just to make sure. Yep, it's going there. Right. Now you'll notice that even if we generate the mesh, okay, it's kind of there, but when I run this, it should give me an error. Right, and it should say, cannot find a node to apply a load. Like I said, load must be on a corner point, a node. So how do we get it there? Well, we can generate the mesh, or we can tell Nastran to generate the mesh according to where that load is placed. Okay, so how do we do that? We simply go to mesh control and we say use a selected point there. And now if you say generate the mesh, you'll find that it generates and makes a node on that point, such that you don't have that error. Okay, this was just a by the way. It's got nothing to do with nonlinear analysis, but it's just something I thought I'd include in this webinar. And now you can apply your load anywhere on that. Okay, so that was just a quick demonstration. And like I said, this is no substitute for any formal training on Nastran. It's just a very brief overview of our Inventor Nastran nonlinear analysis. Okay, so engineers and designers with specific questions can contact us. We can assist with all sorts of simulation needs, whether it be Fusion simulation or Inventor Nastran, any sort of thing. You can find my contact details or just my email at the bottom here. And yeah, if there's any questions, you're welcome to ask now. Okay, if there's no questions, thank you again for joining us. And yeah, you can always get in touch with us should you need any help going forward.